with the physics test?
It was okay. I think I did well.
Okay. Was it okay? Yeah. That's good. And the math test?
It was okay as well.
Only okay?
I mean, it was good. I think it's I think I'm going to be too sure.
Good. Good. Okay, so we're now, new semester, new chapter. No, actually, I have to do the homework for waves, don't I? The last lesson, stationary waves. Okay. So we'll do that before we start something new. Okay. Right, 6 questions. I'll need my calculator. Number 1. A girl is playing a harp. She plucks the 30 centimeter cord and the first harmonic is formed. What is the frequency of the note played? Okay, so that's okay, isn't it? Where's my pen? Here we are. Oh, come on, work. I'll have to draw it. Right, so, yeah. So the first harmonic would look like this. Anyways, if this is 30 centimeters long, what's the wavelength?
This one is the first one, so it's 4.
What's the wavelength?
40.
No, what's the wavelength? 60 centimeters, yeah? Is that okay, Sophie? The wavelength is 60. So you can use the formula V. Well, that's only half a wave if she plucks the string. Yeah? So it's V equals F lambda. So F equals V over lambda. So 340 divided by 0.6. So what did you get, Sophie? Did you do this one?
Yes, but I didn't calculate.
Okay, what did you write?
F equals 340 divided by 0.6.
Correct, yeah, which is 567. 567. My pen's not working. Let me unplug and replug. Okay, so 567 for the first one. Right, number 2. Some wind blows through an open at both ends 40 centimeter pipe. What's the fundamental frequency? Okay, so what you got here, this time the pipe is 40 centimeters long, and if there's a note playing and it's open at both ends, I think it'll be, it'll be like this, wouldn't it? Yeah. So the wavelength would be 2 times this? Yeah. So 80 centimeters. So again, the frequency would be 425 hertz. That's okay, is it? No. A closed end organ pipe is used. The third harmonic is formed at 1100 and the fifth. What's the frequency of the fifth harmonic? Okay, the third harmonic is 1100. Right, so your pipe, it looks like this. You have an organ pipe. Do you know what an organ is? Do you know what an organ is, Sophie? Explain organ. Go on.
It's a part of your body.
No, it's not. It's not that mean, is it? Yeah, but where do you see this musical instrument?
In a lot of scary movies.
True, in scary movies. In real life, where would you see it? In a church, yeah. It's kind of like a big piano with long pipes on it. Do you know this? You probably don't have it in Korea or Malaysia.
Yeah.
It's more of a Western thing. Anyways, it is the third harmonic. Right, let me try my best to draw that. Okay, the first harmonic, I'm going to draw this sideways, it's easier for me. Right, the first harmonic, let me see, this should be node and this should be antinode. Is it 1/4? Yeah, that's the first one. 1/4 the wavelength. So then the second one would be, that's the first one. The second one would be, let me see, I go up, down, down, up, down, down. That's the second harmonic, which would be 3/4 the wavelength. So I can kind of guess here that the third harmonic would be then 5/4 a wavelength. No? I did something wrong?
4/3
Yeah.
and 4 and 5.
Oh yeah, what I'm, yes, sorry, what I'm saying here is how much I have. So I have 1/4 of a wave here. Yeah, and I have 3/4, so the next one means I'll have 5/4. So then I could say that the wavelength would be 4/5 the length of the pipe for this one. Now what else do I tell you? Or do I tell you anything else? The frequency is 1100, okay? So you know that V equals F lambda. So F equals V over lambda, which will equal 340 over 4/5 L. So 1100 equals 340 over 4/5 L. So the length of the pipe uh, 1100 times 4/5 divided by 340, flip it up. I got 0.386 meters. And I asked, I would like the fifth harmonic. So what would be, how much of a wave would you have in the fifth one? Let me see, 1, 3, 5, 7, 9. You would have 9/4 of a wave in the fifth one. So the V equals F lambda again. What do I want? I want the F, is it? Yeah. So the F equals V over lambda. The V is 340. And the wavelength, hang on. What's the wavelength? It will be. It'd be 4/9 the length of the pipe. Okay. So 340 over 4/9 times the length of the pipe doesn't change, 0.386. Okay. And then 1982. Okay, is that okay? Yeah. Next. A woman is working with a large machine which has 2 settings, fast and slow. When its RPM is 240,000, the machine sounds louder. She reasons this is because the stand-in wave is formed in her ear. Assume a first harmonic was formed. How big is her ear? Okay. So what you have here, number 4, this is her ear. And we have a wave inside of it, and this is a length L here. So we have 1/4 of a wave. So the wavelength will be 4L. Now the frequency, I actually give it to you, it's 240,000 RPM. That's rotations per minute. So how can I get that per second? Very good. So I get 4,000 hertz. So L equals lambda over 4, but of course V equals F lambda. So lambda equals V over F. So this is V over F over 4. So I get 0.02125 meters. Or if you want, 21.25 millimeters. So about 21.3 millimeters. That's how big her ear is. Is that okay? Continue. A car is travelling at 120 kilometers per hour between two radio towers. The signal increases and decreases as the car travels between the towers. The signal peaks are 43 seconds apart. What is the frequency of the radio wave? Right, so I'll try and draw this here. What you have happening, you have one tower here, radio station, and another tower here, and they're transmitting a radio signal, and you're in your car, you're driving along, it's a car. It's a car. Now, what's happening here is that the reason it gets louder and quieter is because you have a standing wave between the two towers. So every time you hit a, hang on, this is a node, this is an anti-node, this is a node, this is an anti-node. Where will the radio signal be strongest? At the node or the anti-node? No, the anti-node. This is when you get most signal. Whereas at the node, there's nearly no signal, or not much of a signal. So the car is moving at 120 kilometers per hour. Yep. And the time between each peak is 43 seconds. So how far apart are the antinodes? Well, if you just use your distance, speed, time, you can get the distance is the speed. Now you have to convert 120 kilometers into seconds, which I'll do, meters per second. And it's 33.3 meters per second. So the distance between the peaks is at 1.4 kilometers. Oh, I didn't know it was blurry. You should have told me.
Something like this on classmate then.
Yes?
The girl walking.
Yes, yeah, that's right. Now, if you look here, if you know the distance between two antinodes, what would the wavelength be? Would it be equal to this distance? Half it? Twice it? What would it be?
Equal to twice of that.
Yeah, because the distance between antinodes is half a wave. So it'd be 2 times that. So the wavelength is 2867 meters.
This is something like that, so is it twice the wavelength?
Yeah.
No.
What did you do?
I didn't twice it. I just did that.
Thinking about something else, huh? Now, we can now use the formula V equals lambda F, and here the V is what? It's not 340.
50, right?
No. What's the speed of this wave?
43 times.
It's c. Remember,
Always the same.
it's electromagnetic wave, it's a radio wave. So you can get that the frequency is c over v.
Okay, so if I got that wavelength part wrong, does that mean all the rest is wrong?
We'll see.
Do I get 0?
No, we'll see. We'll see.
What does we'll see mean?
We'll see. You'll get your results shortly, don't worry. Sorry, well, no, you're distracting me. You're distracting me so much. C equals lambda f. So f equals c over lambda, of course. Lambda was 2867. Yeah. So it's going to be 104,634 hertz, but if I divide by 1,000, you get 104.6. The c, speed of light, c is 3 times 10 to the 8 meters per second. By the way, do you know the name of any radio stations in Dublin?
They always say one.
Yeah?
I
So there's one radio station, for example, called FM 104.
That's the most famous one.
Not everybody would know this one. And FM 104, the 104, or like FM 98, or Spin 103.8, all of these are the frequencies in kilohertz. So this FM 104 is 104 kilohertz, or 104,000 hertz, like my example. So you could actually, if you were traveling between two radio towers, traveling at the speed limit between two radio towers, the signal should get stronger and weaker every 43 seconds. But that's only if you're traveling between two radio stations. They must be broadcasting at the same frequency. But this doesn't happen in real life, because what happens in real life is you have Dublin and you just really have one radio tower. But for in some situations, if you have like a national, you know what I mean by national, like the radio must be in every part of Ireland. So we don't have a map. So I don't know, like here's Ireland, here's Dublin. If you take a radio station like RTE, the national station, it must play all over the country. So that, I feel like they must have another tower maybe in the west, like Cork. Maybe they have one in the south, maybe they have one in the north. So that means if you were driving, say, from Dublin to Galway, and there's a radio tower here, and there's the same radio tower here, broadcasting the same station, I think you should get this effect as you travel. Although you're not really going to notice it unless you're paying close attention. Yeah? Anyways, I just thought that was interesting. Okay, last one. So in number 7, you've got your 6, thank you. In number 6, you've got your pipe again, and you've got a standing wave of 1100. Third harmonic, let me try and draw this. Up. Hang on, let me think. That's the first one, a quarter, then three quarters, then 5 quarters. Okay, so it will go up, down, up, up. Okay, so this is the third harmonic, and the wavelength here will be 4/5 the length of the pipe. Then in blue, I'm not going to draw it, it's going to be, well, I'll try my best. The fifth harmonic, hang on, this is 1 quarter, 3 quarters, 5 quarters, 7 quarters, 9 quarters. Okay, so the fifth harmonic will be like this: up, down, up, up, down, up, up, I think. So in blue, the wavelength would be, for this one, I'll write this one here, this is for the third and this is for the fifth. That would be 9 quarters the length of the pipe.
This is going to be 4/9.
It is, thank you. 4/9. Okay? Now, what they're saying in this question is, in real life, if you do this to calculate the wavelengths, it's not going to be perfect, because what's happening is, at the end of the pipe, you have to strike a tuning fork to make the sound. So there's some kind of error. It's not going to be perfect. So the wavelength for the third harmonic is not exact. It's going to be wavelength plus some small error. And likewise for the fifth harmonic, it's not going to be perfectly right. It's going to be the correct wavelength plus some small error. Very small error, like 1 centimeter. Okay, so we also know here that the frequency for the third harmonic is 1100, and the frequency for the fifth harmonic is 1800. Now actually, yeah, I put the error here. Okay? So you have V equals lambda F. So you could say, for example, 340 equals lambda 3 times F. But what I'm saying here is this lambda won't be perfect. There'll be an error on it. Error. Times F, 1100. And then here you can have 340 as well, equals lambda 5, but there's some error, times 1800. Okay. Now, let me just remove the e's here. I don't want to write them twice. I already wrote the errors here. Now, if you look at this, how many equations do I have? 2. But how many unknowns do I have? 3. Lambda 3, lambda 5, and the error. But if I use this, I can change the lambdas into L's, because the length doesn't change of the pipe. So I can change this into 340 equals 5 quarters L plus the error times 1100. And then here 340 equals 9 quarters L plus the error times 1800. Can this be solved? Yes, this can be solved. What's the easiest way to solve this? Yeah, they're both equal to 340. So you can get 5 quarters L plus the error times 1100 equals 9 quarters L plus the error times 1800. Okay, so I'll cancel those zeros there.
5/4.
Should be 5/4, isn't it? Oh, it's not. Thank you, Sophie. I have it upside down. It should be 4 over 5 and 4 over 9. These are upside down. I'm so glad Sophie's here. She always notices my mistakes. Okay, so here I have 44 over 5L plus 11 error. You lied to me. Equating them's not the best thing to do. No, stop, abort, abort. Don't do this, don't do this. Abort. Don't do this. Right, I'll just simplify them. Make yourself useful. Hareen, this should be 4/5. Can you do 4/5 multiply 1100? And then Sohi, do you have a calculator? No, it's okay. I'll do the next one. 4/9 multiply 1800.
880.
What did you get?
4 over 5 times 1100.
Yep.
880.
880 L plus 1100 error equals 340. And then here I got 800 L plus 1800 error equals 340. You learned how to solve these in maths, didn't you? What's the name of this problem?
Simultaneous.
Yeah. So I'll just give you the answer directly, okay? So for L, you get 0.338, and for the error, you get about 0.0386. So the length of the pipe is 33.8 centimeters, and the error is equal to 3.86 centimeters. It's a pretty big error. It's about 10%. Okay, are you okay with this? This last one's a bit tricky, I know. Yeah? Now, if you want, hang on, if you want to be clear, I suppose if you want, you can maybe say that this should be minus, because you want to take the error away from the lambda 3 estimate. And if you wrote minus here, that's fine. And then if there was a minus here, that it would mean that this one would be a minus. But that's not important. Just so you know, for the exam, I've seen this question in the exam twice, but they don't call it error in the exam. They call it the correction term, but it means the error. Okay, we're good? Yep, I'll stop this. So